So in this section, or in these group sections here, we're going to talk about motion as what's called, in terms of a frame of reference, displacement, time, and velocity. We're going to talk about displacement and calculate it for a certain amount of time, and then we're going to talk about position time graphs. And this is what you saw in the summer packet with those two graphs that you saw. So we're going to revisit that concept, and we're going to break it down a little bit further in this section. So first, let's start with frame of reference. So what this is used for is just a way to specify where something is physically in space and when it's occurring in time. So for example, at exactly 9:04 and 45 seconds, I'm exactly right here. So this is where I am in space and time. This is my location. I can say that I'm 5 feet from the wall and 5 feet from the north wall and 2 feet from the west wall, and it's at exactly 9:05 a.m. So that's space and time. Now, at 9:05 and 5 seconds, I'm over here suddenly. So now I'm 7 feet from the north wall and 2 feet from the west wall. Again, you're specifying space and time. That's what frame of reference is. It's all it is. So, with that said, we can also talk about relative spaces and relative locations. So imagine you are on a train and you're on the subway. Let's see, I don't know, for some reason you want to walk away from that end of the train. I'm not going to be rude or anything. So for some reason you just want to leave that end of the train. So you start walking, you're in one train corridor, okay? You start walking in this direction. The train is moving in this direction. So if the train is moving this way and you're moving this way, have you ever done that before? What does it feel like?
It feels like you're moving faster.
It feels like you're really moving faster. It's just weird. Because like everything's moving by you at the rate of the train, but then when you start going, now it's you and the train together moving that way, right? You're moving on a platform that in itself is moving. So it's kind of a weird concept, right? Now, the Earth in itself is also rotating, which is even more weird, but you're kind of in a state of equilibrium right now, even though you're moving at like 23,000 miles per second, some ridiculous rate the Earth spins at, miles per minute. I forget what it is, 20,000 miles per minute or per hour, I forget. Per second would be too fast. But the concept of motion within motion involves your frame of reference. So now imagine you're on the same train and it's moving this way, but you see, I don't know, who don't you like at Loyola? I like me. You see somebody you don't want to see at Loyola, and you turn around and you start walking the other way. You don't want to talk to them. So now the train is moving this way, and you're moving that way. So now what's happening?
Like a sense of gravity coming towards you.
Oh, you have a sense of, your momentum carrying you this way, and you're going this way. But, I mean, like more in sense of velocities.
Negative velocity?
Yeah, compared to the train, your velocity is negative now, right? When you were moving with the train, you could kind of add those velocities together and get a sense of how fast you were moving. Because the train's moving 30 miles an hour, and you're walking 2 miles an hour. Your speed is 32 miles an hour of velocity that way. But when you're going 2 miles an hour this way, and the train's going 30 this way, your net is 28. 30 minus 2, or plus the negative 2. You have a negative velocity. So your frame of reference affects your overall velocity. Right now, the ground is stationary. So if I start moving on it, I could say I'm moving with a negative velocity. I could say I'm moving with a positive velocity. Because I know I am, because this is considered stationary. Even though, again, the Earth is rotating. Okay? Let's see. All right, let's go to the next slide. Displacement. The concept of displacement. It's very similar to distance, but it is not the same. Some of the ideas are the same, but it is not the same. So displacement is simply the change in your position. How would that be different from distance? How would that be different?
Well, displacement doesn't matter how far you go. It's just where you start to where you end.
Very good. That totally makes sense. Have you ever said the shortest distance between A and B is a straight line? That's exactly what Gabe is saying. Doesn't matter how far you go, it matters where you end up. That's what displacement is. What's distance? What's distance? It's how far you go. Exactly, very good. So it's how far you travel physically, whereas displacement, as Gabe said, is your actual change. So ready, I can do this, would say like 4 feet, another 4 feet back, about 8 feet travel. But my displacement was merely a foot to the right. 1 foot to the right would have covered the same thing as doing this. Why do I want to do all this work to get here? Displacement is the concept of jumping from A to B. So displacement is the straight line distance between any 2 points. Okay, yeah, this is what's given here, but that just, it change of position is the easy way to say it. It's the straight line distance between any 2 points. Distance traveled is the path taken. Okay, distance traveled involves the path itself taken. During the year, we're going to use X for displacement. And its units, we're going to put units in brackets, are meters. Throughout the entire year, you're going to see me use brackets. That just means units. Maybe write that right now. Brackets mean units. In your textbook, it's the same way. In almost any science book, brackets or bolded, sometimes bolded text, like a bolded M, indicates meters. And the variable is X. So jot that down, please, also. Brackets means units. Okay, the variable is X, brackets are units. So you might say that the change in displacement is delta X. Look at the diagram, right? The change in position or the displacement is considered delta X. A lot of books use delta X. A lot of books use X. I don't care which one you use. Know that X means change in position or simply displacement. But think about it logically. If you want to find the overall displacement, you would take the final position minus the initial position. That's the easy way to think about it. So what's the gecko's displacement here? Or lizard, or whatever this figure is. What is his or her displacement? Approximately. I'm not asking for the exact answer. Approximately, what's the displacement? Somebody besides Gabe has answered a few more. I appreciate it. George, go for this one.
Probably like 60.
60. You have like what? 84 and 24. It's about 60. Good. Okay, final is 84, initial is 24, 84 minutes. 24 is positive 60. Now, follow that up. Nick, what if instead of a gecko going this way, the gecko went this way? How would it differ?
It would be a small number,
Small number, but more specific. I mean, the gecko goes 60 this way right now. What if the gecko goes 60 this way? How would it change? How would the displacement change?
Zero.
Not zero. Be careful. Think of a number line. 60 this way on the number line.
Oh, negative.
It's negative. Good. It's just negative. So this is the key. Displacement, the direction of motion matters. To the right is positive. To the left is negative. But for distance, direction does not matter. Maybe jot that down. For distance, direction does not matter. It's simply the length of the path taken. For distance, the direction does not matter. Okay, it's simply the length of the path or curve taken. Displacement, to the right is positive, the left is negative. Same for displacement, consider up positive and down negative, please, for vertical displacement. Okay, vertical displacement, up is positive, down is negative. And honestly, it doesn't matter. If you wanted to go crazy all year, like my teacher told me the story. I don't know if I believe my teacher, to be honest, but he told me the story. I'll tell you. He said that he once had a student, because I was in his class for 2 years. I had him for physics and then AP physics when I was a senior. He told us that he had a student that thought this kid thought he was so smart that he would try to annoy the teacher by considering down positive and up negative, and right negative and left positive for everything he did all year. And theoretically, you'll get the same exact answers. It's amazing to think about it. It's arbitrary that we call up positive and down negative, and right positive and left negative. It could have been the complete opposite, and mathematicians could have completely gone the other way around forever, and the world would still work the way it is. Everything would just be switched, right? If you think about it. So he had a kid who would always call down positive, saying, well, everything accelerates down. You want to go down. And some textbooks actually do consider down positive, but most of the time, almost always, right is positive and left is negative. The up and down is the one that can switch. Okay, but for you, I would recommend, honestly, just trust me on this one. Let's say everything to the right is positive and left is negative, up is positive and down is negative. It just makes life easier because as we speak about these numbers in class, the sign on them matters. velocity of positive 5 is different than a velocity of negative 5. And if we have different interpretations of negative and positive, then we're going to have miscommunications. Okay? So that's why I would say to do that. Let's look at an example. This is a conceptual example. This is the kind of question you can expect on a test where it's conceptual. No math involved here. No math necessary. Take about a minute or two to think about it. How many people think they know what it is? All right, then talk to the person next to you for a quick second and see if either of you know. Just out of curiosity, see if everybody knows and every other. We can explain it. We can explain it. What's that? Hopefully, right?
Okay. The displacement's the same.
Displacement's the same. That's correct. Explain why for that one.
Like we mentioned, even though the astronauts went around the Earth multiple times, they would have more distance, but not more displacement because they both ended up at point B. So.
Yep. They
point
both.
B, California.
Exactly. They both did the same thing in position. They both went from Florida to California. So the red trail of the photographer, although it's a shorter distance, is the same displacement. The distance traveled is much greater by the astronauts who went around the Earth a bunch of times, because you would literally count the curved distance that they traveled. It would be like, say, 5 or 6 circumferences plus a little more of the Earth in distance. Whereas the photographer's distance might be, 2,000 miles? Is that around? No, 3,000? Right across the U.S.? 3,000? So about 3,000 miles, say. That's the distance for the photographer. And his displacement is about the same. Actually, his distance is more, really, right? Think about an airplane. Here's the airplane, lifts off in Florida, comes down in California, right? Distance is more than displacement, isn't it? Displacement is a straight line. If you put anything that's not a straight line compared to a straight line, it's always going to be longer. Imagine this straight line and being on the straight line the whole time and deviating just for a second. That line is longer automatically. Does it make sense? Because you're going a little bit further by deviating. The shortest distance between 2 points is a straight line. That's displacement. So the plane, although it went up and came down, has the same displacement as the astronauts who ended up here. It's a straight line. Okay? All right, let's quickly talk about the concept of positive and negative because we already alluded to it. Motion to the right is positive. Motion to the left is negative. So it does not matter where you start. Even if I start in a negative location and go to a further negative location, or if I start here in a positive location and go to a negative location, if I go to the left, the concept is that it is negative position or negative displacement. Okay, so to the left here and these ones to the right. Yeah?
Using that in context of the last example, if the astronauts went around the other way, would that be negative?
Yeah, it's a great question. For displacement, in this case, because of the fact that the surface that you're on is curved, it's a little bit different. It's more of a three-dimensional displacement. So you have to consider x, y, and z, all three. Now, Realistically, no, it's the same displacement. Because even though they started here and ended here, even though they went this way, it doesn't matter because a circle has a cyclical pattern, whereas linear distance does not. You can't say the same about motion that way and motion backward because you're never going to get back to the location you started. We are assuming for local motion that we're on a flat surface, right? Even though the Earth is curved. So the minute you have this kind of motion, your displacement and the concept of displacement is very different there. So we're just speaking generally here, but if you really think about it differently, it's rotational displacement also, so it's a little bit different there. Okay, but we're going to say for now that if you end in the same spot that the other one did, you'll say the displacement is the same. We'll assume flat distances, which is a huge assumption, obviously, one that, a lot of explorers made incorrectly for a long time, that you're on a flat surface, even though the Earth is curved. Good question. Other questions at all? Let's stop there for today. So we spoke about rates already. You guys already took a chance to look at that in your summer math packet or summer physics math packet. We're specifically going to talk about average velocity here. And what do I mean by average velocity as opposed to like instantaneous velocity? What's the difference between average and instantaneous?
So average is over speed on time, and then instantaneous is at that exact second.
Yeah. An average velocity is over a certain period of time, and instantaneous is an exact moment. So when you're driving your car, okay, for those who drive, or if your parents are driving on a trip and you're looking at the speedometer, when you read the speedometer, which one is that? When you read the speedometer in your car, which type of velocity is that?
It's instantaneous.
Instantaneous. It's the exact velocity at that moment in time. If you wanted to find out what your average velocity was for the entire trip, you need to figure out your total displacement over the time period. Now, that's different from average speed and instantaneous speed. That's the other thing we have to talk about. We're going to see that in a moment, the differences between the two. So let's start first with average velocity. X is going to be our variable the whole year, X or Y, it doesn't matter which one, for displacement. Okay, so you can jot these things down. What we're talking about is up to you. X is displacement. From last class, what was displacement? What was the definition? Not my words, but in your own words of displacement. What is displacement? Displacement. Lauren, help us out. What's displacement? How is it different from distance?
So like displacement is like it's like the straight distance between the two points. So like the distance is like the actual like mileage or like
Yeah, very good. So again, remember please that here's New York, and you're driving down to Florida. You're taking I-95 the whole way. Is I-95 a perfectly straight road? Is any road a perfectly straight road? Good answer. No. Even if you think they're perfectly straight, they can change elevation. So no roads are really perfectly straight. So let's say this is I-95. I don't know, okay? The displacement would be the dashed line. That's the displacement. Okay, again, the distance traveled is the solid line. So in this problem, or in this case, when we talk about average velocity, we're not talking about average speed. Average speed would be different. And we're going to see in a moment how average speed would utilize the distance traveled, whereas average velocity utilizes the displacement that the object undergoes. What is t, obviously? Everybody, what is t? Time. Okay, what's in bold there on the side? What do those represent again? Meters over second. Those are our basic standard units we're going to use. So when we're talking about displacement, we are going to talk about displacement in terms of meters. When we're talking about time, in terms of seconds. There may be prefixes on these. It may be kilometers, kilometers, right? Kilometers, kilometers, 1,000 meters. Seconds, it might be milliseconds, because maybe you're looking at a reaction, a chemical reaction occurs at a very, very, very fast pace. So it's measured in milliseconds and not seconds. So your prefixes may change, but those are going to be our standard units for velocity, meters per second. Questions on? Yeah? Yeah? All right, let's look at the first example. So during a race on level ground, Jamie drives her go-kart with an average velocity of 6.02 meters per second to the east. What is her go-kart's displacement in meters after 2 minutes and 17 seconds? What is the displacement in meters after 2 minutes and 17 seconds? So there's an approach I like to go through with all problems that involve math. And the approach is really simple. So if you want to write down the approach for the first problem we do today, and then utilize this for the rest of the year, it'd be very useful. So the first thing that you want to identify, anybody know, what do you identify first? What's important in this problem?
The fact that she's gone 6.2 meters per second.
So 6.02 is very important, for sure. For sure. So is 2 minutes, 17 seconds. What do you call those things? The problem? Variables. They're going to fall into variable locations later, but they're not the variables involved, really. In your math class, your teacher would say, if the problem presented too much information, it was considered extraneous, right? The information that the problem gave you were called the givens. Have you ever heard that term before? It's a way to provide like an idea of what the problem gives you physically. So let's start by listing our givens first. It's always the easiest way to approach. List the givens. The minute you list the givens, it will help you to choose which formula to use. Right now, you have one formula. So you know which formula you're going to use. We're only literally covered the first formula on the formula sheet for the whole year. That's all we've looked at so far. So right now, we don't have to worry about it too much. But the givens later on in the year will help you to choose the formula that you will use. If I'm given, I know for personally, if I'm given mass, if I'm given another object's mass, and the distance between them, I would know that I'm probably going to calculate the force of gravity. Because for me, I know gravity is g m over r squared. If I have m and r squared, and g is a constant, that's the only thing I could solve for. So the givens help you to pick the formula you're going to use. So we list our givens. What is 6.02 meters per second east? What is that as a given? What does that actually mean? 6.02 meters per second east. What is that exactly? Say again? It'll be positive. East means to the right. West means to the left. So we know that it's positive. What is it? It's positive. It specifically. What variable are we talking about? Or what term are we talking about? Good. The rate or the velocity itself. So let's start with velocity here. Now I can write the word east, or as Juliet mentioned, I could just leave it as positive. If it were to the west or to the left, you would say negative 6.02 meters per second. Remember, we talked about this last class. Displacement, it matters which way you're moving. So velocity, because it's a function of displacement, right? Velocity is a function of displacement by looking at the formula on the top right. Since displacement matters whether you go to the right or left, velocity also matters whether you go to the right or left. And then the other piece of information that's given. The other piece. What's the other given?
2 minutes and 17 seconds.
Now, for the sake of this problem, am I going to use 2 minutes and 17 seconds of my time? Gabe, continue.
I just want to use 77 seconds.
You want to convert it all, so 2 minutes, so 137 seconds. You did 1 minute.
Oh, shit.
That's all right. 137 seconds. What's 2 minutes, really? 60 and 60, right? 120. And then add your 17. So that's the number we're going to use. Gabe, you answered the question. Somebody else answered this question. Why do we have to use 137 and not 2 minutes, 17 seconds? How come?
Because you're doing meters per second, so you can't really measure seconds in minutes.
Absolutely right. Look at your velocity. Your velocity is measured in seconds. That's why in this class you're going to hear me talk about units, units, units. They tell you what to do with the problem, the units. There is nothing measured in minutes here when it's referring to velocity. There's nothing about minutes here. So either we can convert this to a decimal in minutes and then convert this to minutes, or just convert this to seconds, and now we're all in seconds. It's the easier route to take. Okay?
Everything's set up.
Perfect.
Yeah.
Try and finish this on your own real quick. Solve for the displacement. Now, it's up to you. I'm going to let you do it on your own, actually. You can plug in numbers and then solve for x, or solve for x first and then plug in numbers. Whichever way you'd like to choose. If you were comfortable solving for variables on the math packet in the summer, then you should just solve for x and then plug in. If you like numbers better, plug in the numbers first and then solve for x. Try it yourself real quick, see what you get. Let's make sure we all get the same thing. This is probably the simplest you're going to see. and your calibration is on as well. So this is 0 here. So you start about a little bit away from it, and move to right hand, move to right, move to right, and then back. Awesome. So we'll see the ones we want to do that will set up. You don't want to stick to a sleep, so I have to make sure I monitor it. Can you run that real quick over it? You know? That's pretty much it, man. I'm just going to check through this real quick. Thank you so much. So I'm going to put both solutions or both methods, solving generically first, and then the other way I'll put plugging in numbers. What do you think the unit should be for x and the answer? Just meters, because it's a length. Remember, x is displacement. It's measured in meters. Focus up here, guys. Come on. X is displacement. It's measured in meters, not meters per second for x. So if you solve for x, how do you get x by itself? Be careful, because you don't... Remember, you're not switching these two this time. You're not switching. You want to get x by itself. Amaya? By?
Well, I did by C.
Good. Remember, x is in the numerator. You don't have to move it. If something is in the numerator, don't ever move it. Get rid of the denominator instead. So t is gone. So x is simply going to be t times v. Oops, equals. So go ahead and plug in your velocity and your time. Here's what you're going to notice. Your time is measured in seconds. Your velocity is measured in meters per second. It's not a coincidence again, It's not a coincidence again that this happens. The whole concept here is that the units have to balance. So what happens here? What happens to my units? What? Seconds cancel out. If that's not obvious to you, you need to go back, look at dimensional analysis again, and see what we did there. Look at the seconds. Seconds up top, seconds down below. It's like x over x. The x's would cancel, right, as a variable. Seconds can be thought of as a variable in this case. They cancel, leaving behind meters. What is my answer? What is my answer?
824.74.
Give me nearest tenth, sorry. 824.7. Agreed? Now, if you chose not to solve generically for x, and you started with this formula, I'll do it on the right side. So let's say you chose not to solve for x. You would plug in velocity here. Fast. Okay, and time there. And we would simply solve for x. Thank you. Okay, solve for x. How would you solve for x again? You'd multiply by 137, getting the exact same answer. If you like plugging in and then solving, that's fine. You can do that. There is going to come a time in the year that I'm going to tell you that it's very useful to solve generically. And you're going to use that method, and then you're going to use, remember substitution from the packet you did? And then you're going to substitute this definition of x as dt into another equation. But that'll be as we get to more difficult stuff. For now, either method is fine. Plug it in and solve, then plug it in. Either way you want to do it is fine. Okay, your answer must have the correct units. If you don't want to put units in when you plug in, that's okay, but I would recommend it because you can see the cancellation of the units and the simplification leading up to meters as your units for your answer. If you don't plug in your units, as I showed you over here, I purposely didn't plug in units so you can see this, you may not know what your answer unit should be, right? But seeing it here is so obvious. Seconds cancels with seconds, leaving behind meters. All right? So make sure as you practice this, you understand what you're physically doing. Questions on this? All right, let's go to the next thing we're going to talk about. Yeah?
So, like, I got the right answer. Going earlier, I think last week, I got going to check when you're multiplying and crossing out. You know how we did last time, where we multiply the numerator and then did that. So
But there was no denominator there, so what could you divide it?
I thought like every denominator was 1.
That's fine, but when you divide by 1, it's the same number. Yeah. Okay, so just be careful with that. Yeah, it's a good way to think about it, Ernest. That's what you should be doing, yeah. But there was no denominator there. So let's talk about velocity versus speed. Let's discuss the differences here. So again, earlier I talked to you about the fact that if you want your average velocity of a trip in a car, looking at the board here on the side with the whiteboard, the dashed line would be your displacement. The solid line would be your distance. Which is greater? Which is greater? Well, distance. Isn't it obvious? Distance is absolutely greater here. So if I want to find out what my average velocity is, I take the displacement over time. That's the formula we just looked at. What might you suppose average speed is calculated by using? It's analogous. It's analogous. What does analogous mean? You know that word? Kind of the same. Okay. It's a decent definition of analogous. It's analogous. Yeah, very good. That's all it is. Let's write that one down. Speed is simply distance over time. Speed is simply distance over time. And it sounds like it's the same thing, but it's not. Again, because the distance traveled is the solid path, the displacement was the dashed line. Okay, I'll put it on the overhead here so you guys can see if you're looking at this later. Distance traveled versus, in blue here, displacement. Okay, straight line from A to B. So again, the speed, I'll write in red, the speed is the distance over time. That's all it is. Now, what's really important, what's something that we should talk about is this. Distance is a measurement of length only. It is not a measurement of direction. Take a look at me real quick. If I do this, my distance traveled is about a meter. If I do this, my distance traveled is about a meter. As opposed to this, my displacement is 1 meter east. My displacement is 1 meter west. You see the differences there? I'm indicating a direction when I'm talking about displacement. So since displacement is used for velocity, direction matters, like we saw in the previous problem. Juliet told us when it said the velocity was east, we assign a positive sign. For speed, look at me. I'm going in an arbitrary direction. I'm walking all the way around, and I might have traveled 30 feet just now. What's the direction I traveled? Nobody has any idea, really. It doesn't matter. The direction traveled for distance does not matter. You can walk in a circle, end up where you started, you would have no displacement because you ended up where you started, right? 0 displacement. Kind of weird. But the distance would be the circumference of the circle. So for speed, since distance has no directional to it, speed has no directional. Again, jot this down. Velocity and displacement, the direction traveled matters. Velocity and displacement, this first formula, put a little note that the direction traveled matters. For speed, which refers to using distance traveled, the direction does not matter. The direction does not matter. Some students like to think about this, and you can think about this for instantaneous speed and velocity. Let's say that I'm driving a car, or let's make it actually a better problem. Let's say I've dropped an object from the top of a building, a 3-story building, and at a certain instance in time, the object is here, and its velocity at that instant in time is negative 2 meters per second. Why is it negative? Why is it negative first? Well, because it's falling down, and we said that down is negative. We talked about this the other day. If you can remember that, you should write that down. Write that down. That down is indeed negative. So the velocity is negative 2 meters per second. The velocity is negative 2 meters per second. What's the speed? What's the speed of that object at that instant? What's the speed of the object? Not 0. It's moving, right? It's moving. It's moving down. But what's the speed? How does the speed differ from velocity? It's just 2 meters per second. Positive, you could say, yeah. Remember, speed does not matter which way you're moving. So if a question in the text asks, the velocity of an object traveling is negative 2 meters per second, determine its speed, it's almost like the absolute value. The instantaneous speed of an object is simply the absolute value of its instantaneous velocity, always. It does not apply for average velocity and average speed. That's totally different. So this trick, you can't find the average velocity and then just take its absolute value and say that's the speed for a trick. But for instantaneous, I'm talking about instantaneous, for the speed at that instant, you simply take the positive of whatever it is. Again, instantaneous speed is really just the absolute value of the instantaneous velocity. Instantaneous, I'm talking about at that instant. Yes?
I have a question. So, like, let's just say you have like a target, and you throw the ball past the target, and then you throw it back, like to the target. Would like the distance? That would be increasing, right?
So you take an object, so let me go through this. You throw it past the target, somebody picks it up and throws it back to you,
No, it throws it at the target, like it reaches the target.
and it then reaches the target.
Yeah.
So the distance traveled by the object does increase, absolutely, but the displacement,
It would be like negative.
very good, the secondary displacement would be. So let's do that example, think about that. I throw an object to the garbage can, I miss, and Nick happens to be standing on the other side. He picks it up and tosses it back in. When I threw the object, I threw it with a positive displacement to the right. Nick picked it up, threw it with a negative displacement back into the can, absolutely. But the distance for me was positive, and the distance traveled when Nick threw it was also positive. Because distance is always positive. Okay?
All of this space would be right like that from visual, as you said, right and left, but it's more straight. Unless you look at
You're thinking right, left, up,
Yeah.
down. That's how you have to visualize. So if an object goes like this, like a football kicker punts the ball, or a soccer goalie punts the ball out, it's moving in the positive Y,
Yeah.
and it's moving in the positive X, both. And that's called projectile motion. I'll get to that in chapter 4. But it's two-dimensional, so yes, right now we're thinking about linear motion. We're thinking about linear motion.
So S equals d over t is average speed, right?
Correct. That's a great point there, Gabe. We should put a little.
What is instantaneous?
Yeah, so that's average speed. A little bar over the top means average or constant. Okay, average or constant here. Some teachers will also put AVG, but I like to use the bar. And then this was the other one. Okay, average velocity. But what Gabe is mentioning is this. Gabe is saying the following, that speed, being the instantaneous speed, is simply the absolute value of the instantaneous velocity. It's very difficult to denote instantaneous. So if you want to put in parentheses out here, and if you had trouble spelling that word, just to write it down right the first time, instantaneous, okay? So the speed at any instant is the absolute value of the velocity. But for an average trip where time has elapsed, not at an instant, but where time has elapsed, we use the formulas on the right. Questions on this? This is a very important topic. So if you're wondering or not certain about something, you can come out, somehow verbalize your question or come up with your question. Let me know, please. Sometimes it's hard to ask a question, I know that. Because you might not know what to ask always, you know? If it pops in your head or if something else confuses you on the next thing, let me know. Okay, let's look at another one now. Let's take a look quickly though, and we talked about this the other day. We talked about the slope, but let's talk about it quickly one more time. If we look at the slope, we think about rate of change. We think about rate of change. And we talked about this in class the other day, that the slope of the line was the velocity. This was on your summer packet. The slope of the line was the velocity. Let's say for now we have a graph of an object's position as a function of time. Let's say that the object follows the following path. Okay, we're going to make it a little bit tougher here. So the object starts here, away from the origin, moves. Then what happens? Stays at the same x, or the same location. So stationary. And then what does the object do? It either drops, or if we're thinking left to right, it goes back to where it started. Think left to right. I know this is difficult because you're thinking vertical motion right now. Forget vertical motion. Think left to right only, please, because it's going to make it more difficult with vertical motion. So, let's say for the example of this problem, this is the origin. Okay? It's weird, but visualize real quick. You don't have to write this down, just watch what I'm doing. The podium is the origin. The podium is the origin. Now, if the podium is the origin, should I be standing at the origin according to this graph to start? Where does this graph start? And there's no numbers for a reason. It's fine. It starts away from the origin. At some positive distance away from the origin. Do we all see this? It starts at some location. If I had increments, you could tell me that. Let's say, for example, for this now, let's pick numbers. Why isn't this working? There we go. Okay, let's say those are our numbers right there. Let's say the units are in meters. So here's the origin. Where should I start? Should I start right on the origin? Where should I start then? 1 meter, and since it's a positive value, to the right. If it were below the axis, it would be to the left of the origin. And by the way, I'm talking about a number line right now. Do you all see that? Visualize a number line? Imagine a number line in front of you in the room. Actually, forget imagining, we'll do it. Make it easier for you guys. Here's the number line. Here's the origin. Okay, here's 1 meter, 2 meters, 3 meters, 4 meters. So according to this is the origin right now. I should be starting here, right? And what should I do? I should advance 2 meters. How do you know 2 meters? It lines up with 3, so why not 3 meters?
Because this from 1 to 4 it's 2.
From 1 to 4, it's 2?
Wait, sorry, from 1 to 3 it's 2. Sorry.
Good. Explain your answer, that's why I'm asking. So from 1 to 3, I have to go 2 meters. So I have to do this in how long? Do I know how long? No, so I should probably do that, all right? Let's give a time period. I'll make it easy on me. I'll make it real easy. Okay? Make it real simple. So Matei, answer again. 2 meters and how long?
2 meters and 3 seconds.
I don't know. Go up to here and go straight down. What does that line up with you?
Oh, that's 2 seconds.
2 seconds, yeah.
I was thinking
Right?
the other side.
3 is kind of over here still, right? So here's the motion in the beginning. Ready? In 1 second, in 2 seconds, I'm here. Now, once I get here, what is my current position? Where am I physically on the graph? Am I at origin? Am I at 1 meter? Am I at 2 meters? 3 meters? Where am I right now? Physically, where am I? Where am I putting a hand up? Where am I running? Where? I'm at a 3 meter mark. And look at the board if you don't see it. 1, 2, 3 meters. That's where I'm at. Now, once I make it here, what do I have to do? I have to stay here. I have to stay here until I get to this time. And then what do I do? Until I get to the x-axis is the origin now, think about it. So here's what's happening. Let me do this motion one more time. So I start in time. I take 1 step. I take another step after 2 seconds. I wait for like 1.5 seconds to elapse. I start going back. I get back to the origin in about 1 second. So I run back to the origin, and I continue past the origin for another second, pretty much there, until I get to 5 seconds. So do you see how it took me 2 seconds to move 2 meters here? But look at this. I moved an entire meter back in almost just a second. So when I went back, sorry, not an entire meter, I moved an entire 3 meters almost back in a second. When I moved back, what did I do? Did I move faster or slower than when I moved this way? Faster. It was obvious, wasn't it? Why is it obvious from the graph that I move faster? It has a higher what? What's the word we're looking for? Slope. Good. And it doesn't matter that it's negative. I'm glad you ignored that. The fact that it's negative, the slope means I moved which way? Left. For now. Left and right. Down actually. Okay? So positive slope. Let's write little notes here. Let's write ourselves some notes. Ready? So the slope here is positive in that region. What's the slope here in this region? Negative. What about the slope in the middle region? What's the slope there? Everybody, what's the slope? If everybody doesn't answer, we got problems here. What's the slope in the middle? What's the slope in the middle region? It's just 0, yeah. It's just 0. Yeah, we call that undefined. And you'll see more in math that you call it infinite soon. But the slope here is 0. So you've got positive, 0, and negative. So again, look at the top. The slope is really the rate of change. The slope is really the velocity. That's our conclusion, really. The slope, if you want to write this down in words, you can. Some people like to write exact words. The slope of a position time graph is the velocity of the object. The slope of a position time graph, that's what this is, position or displacement. Position, displacement are very interchangeable. The slope of a position versus time graph is velocity. What's that?
Isn't the slope also the speed though?
Be careful, because the speed doesn't matter which direction you're traveling. Where notice here, it does matter the direction. Okay? So could you tell me this? Answer this question. This is a tough one. This would be a question that's definitely on your lab. Where, Matei, because you answered this question, where would the highest speed be? Where would the object have the highest speed in this problem? Did you? In section 3, why? It's going down to 4, okay, but give me more specifically about the math involved.
It drops 2 meters or 3 meters in just a second.
It covers a distance of 3 meters or a displacement of 3 meters in only 1 second, whereas earlier you moved 2 meters in 2 seconds. So you could say that the what of this line is greater? The slope. The slope. Whichever part of the line has the greatest slope, I don't care if it's negative or positive, is the greatest speed. Is the greatest speed. So the slope here, let's calculate the slopes. This slope, you go up 2 over 2, so the slope is 1 meter per second. Everybody agree with that? If you found the slope there. 2 divided by 2 is 1 meters per second. How about here? Drop 3, so negative 3 is the change in vertical, right? Change in vertical is negative 3 over positive 1. So the slope here is negative 3 meters per second. So which one has the greater slope? And I mean the magnitude. We're going to use the word magnitude this year. Magnitude just means the number portion, not the direction. Which has a greater number? Obviously, I didn't have to ask, it's 3. Don't even look at the sign. When you're trying to figure out which one has the greatest speed, you look for the biggest number. Forget the sign. Is that clear? So the biggest speed, as Deidre told us a moment ago, is in the third section. The third section. Where is it moving at the slowest speed? At the 0, very good. In the middle section, right at 0 velocity. What happens when you have 0 velocity? What are you doing again? You're not moving. No motion whatsoever. Questions on this? All right, we're gonna do more with this today, and you're gonna see that in the lab. It's gonna apply this also. Let's take a look at example 3. A book is moved on a table around the edges of the table. The dimensions of the table are 1.75 meters by 2.25 meters. If the book ends up in its initial position, what is the displacement? If it completes the motion in 23 seconds, what is the average velocity? And finally, what is its average speed? Okay, what is its average speed? I'll give you a minute. List your givens on your own. I want to see how you do with this. This is a problem where you might want to draw a diagram. Part of your givens are geometry. You're going to see that throughout the year. Geometry is very useful in physics. I would recommend a diagram. You don't really need it if you can visualize it, but a diagram might be useful because it can alleviate some common mistakes I've seen over the years. So it may be useful to draw a diagram, and then you can draw the motion of the book on the diagram. When you're done with the diagram, list your givens. List what is the displacement, what is the distance, what is the time. Those are all given. Whether or not they're given directly, they're given actually. These are not given directly, but they are given. Displacement and distance are both given here. Nick, tell me, what's the displacement of this problem? What's the displacement, Nick? Think about what displacement means. A change in the object's position from beginning to end, an overall change.
So it would just be
We're going to do 1.75. I want somebody to not give the answer, but to give Nick a hint. Don't give the answer. I want a hint. I do not want the answer. I want a hint. Plaza, what's the hint?
It's a straight line from, it's the total distance traveled from the initial starting point
Two. To the ending point. His hint is that displacement is the actual straight line distance from initial point to ending point.
So wouldn't it be 0 then? Because it's, yeah, it's a
Okay, so ready? Motion. Starting here. 1.75 meters, 2.25 meters, 1.75 meters, 2.25 meters, but I end back here. So the displacement turns out is 0 in this problem. Nick, what's the distance traveled? Now that you definitely understand. And again, think of the motion. Tell me what you would add up. You don't have to give me the exact answer.
Alright, then you do 1.75 multiplied by 2 and 2.25.
Good. And personally, Nick, what I would have done is added the numbers, then doubled to make it easier math. Do mental math. 175, 225 is 4, and then just double it. So again, what Nick is saying is that you are traveling around a rectangle. There are 4 sides to a rectangle. So you go a distance of 1.75 meters twice, a distance of 2.25 meters twice. So really it's 1.75 plus 2.25 plus 1.75 plus 2.25, inherently giving you 8 meters of distance traveled. All right, that's awesome. We got that. Time is given. I'll write that down at the top. Now, once I have my givens listed, think back to the last problem. What did we then list? What did we then list? We might not have actually gone into this detail, so maybe I should write this down. What I'd like you to do after is list what you're looking for. So what are we looking for here? I don't think we did it last problem. What are we looking for? Because now we're looking for 2 things. And what else? So we can write that down. So we've got the first section, we've got our givens. The second section, we've got our desired variables. The third section, we should probably write down how we're going to figure it out. What do we need to figure it out? Formulas. The third section, let's list our formulas. And if you don't know these, look at your last slide. We wrote them down 2 minutes ago. Okay, there's our formulas. And finally, our fourth part. So here's how I set up your problem sets, by the way. If you look at your problem sets online on Moodle, you'll see the assignments already listed there. Everything's listed, so you know what you have to do. In this, what did your problem set do for this section? Anyone remember? Yeah, the day before the test. That's Wednesday. So you should have been looking at this or thinking about getting a head start. After today, you'll be able to do it all. 2-1, 2-2, 2-3. You could have already done the problem set work from 1-3. But in your problem set, I put something called problem set format. And for each problem, I write down, list the givens, list the desired variable, list the formula used, show the generic solution, and then substitute. Do I have to do anything for velocity? What is the answer for average velocity? What is the answer? And it's very misleading. It's 0. Because your displacement is 0. Remember, technically speaking, your position has not changed. You started here, you ended here. So no change in position means no displacement. No displacement means 0 average velocity. It's very misleading. So really, if you traveled from New York all the way to Japan and then came back to New York, your average velocity is 0. Doesn't make any sense because you're used to the word speed, average speed. Okay? The average speed in this problem would be calculated by taking the distance traveled over the time period, oops, not 2.7, but 23. Maya, go ahead. But 23 seconds, giving us an average speed of 0.35 meters per second. Notice, no positive or negative sign there. Because again, speed only matters the distance traveled. The distance traveled does not need an indication of direction. This is always going to be listed as positive. Take like a break if you need water. We're going to come back, finish this example. So, two students walk in the same direction along a straight path at constant velocities. What does the word constant velocity mean to you?
You mean the same velocity?
The same velocity. Constant in math is something that doesn't change. So if something is constant, it is not ever going to change. Use crappier words. Say that. There's like, yeah, that's a nice word. Use, there's fishing twine and stuff. Yeah, use that. So what we're going to see here is that we have two students that are doing this. One is doing this, 1.5 meters per second, and the other is just a little bit faster, 2 meters per second. But are they accelerating? Are they accelerating? No, they're not. Why aren't they accelerating? We haven't gotten to acceleration yet, but we've alluded to it already. Acceleration indicates what? You must have a what?
So like keeps on starting time and then over time you increase the speed.
Yeah, and we said here that it's a constant velocity. So since there's no increase or decrease in velocity, the velocity is constant, so there's no accelerated motion here needed. Now, we know that that they start at the same time, and the question says how much sooner does one student arrive than the other? So this is a very easy problem for you. This is really, you could have done this in your summer packet. What do you need to calculate? Give me the overview of this problem. I'll let you do it all on your own. What is the overview? What do you need to figure out to get the answer to this problem? You need two things to figure out. What are those two things you need?
You need displacement. No.
You're given the displacement.
You need velocity.
Ernest, help me out.
You need rate and then you need the distance that it's traveling.
Yeah, guys, those are the givens. I'm asking, what do you need to solve for? What are the two things you need to solve for?
The time to get
The time and the what?
good times.
Yeah, the times, thank you. The other time. There are two times, right? Student A walks slower, so that's time number 1. Student B walks faster. That's time number 2. What are you going to do those answers when you get them? Subtract. So go ahead and do this problem twice. Once for student A at his or her velocity, once for student B at his or her velocity. Calculate the time 1 and time 2 completely separately, and then simply subtract the 2. Try it on your own, please. Again, list your givens for each scenario. List what you're looking for each scenario. Put your formula for each scenario. Solve generically, which is the same generic solution for each scenario. Having trouble? All right, where's the... So maybe like this here. Hold here, and don't even worry about this. Just kind of scissors, much more.
That part is good.
Yeah, that'd be good. Here and here is good. This is going to go around the neck. And you use what word would you have? Around the neck, around the neck, and like, you know, comfortable. I have orange
We
ones.
used to check if you get
Only problem is I usually burn the ends to make it not fray. Yeah. So you might have to do this. Bend the rope like this and push it through the hole. You know what I'm saying? And then pull it through that time. Oh, like right? Right? Sometimes I do that. Just say to me, I got it. I'm good. Thanks. So we know that they're moving the same distance. So in this case, distance and displacement are really the same. Solve generically, right? So that's what we know. What are we looking for? Time. Our formula is this in both cases. What should we solve for? What should we solve for? T. So, switch those two right there. It's the same solution for both. And then we just plug in our different numbers. That's all we have to worry about here. So x, which is 500 meters, over 1.5 meters per second. 500 meters over 2 meters per second. What happens to meters? What happens to meters? What happens to meters? Right. They cancel. Leaving behind what? Conveniently. Seconds, because you're solving for time. You're solving for time. You've got 333 and a third seconds and 250 seconds. How do you get your final answer? Subtract. 333 and a third minus 250 gives me 83.3 or 83 and a third seconds, which is 1 minute and 23 and a third seconds. Okay, it doesn't matter which way you want to write it. Now you can leave it like this in seconds or minutes with seconds. It doesn't matter. Questions? Yeah.
For seconds, I remember you said that for seconds you just divide it by 60, right? Or you multiply by 60.
To convert, well, just don't memorize it. Just do it if you have to. Ready? Here. Make it easier on yourself. If you have 60 seconds, you want to think about per minute. You have, well, in this case, sorry, I shouldn't say that. Well, the problem here is that you have to consider 60 out of 83 being 1 minute, and then subtract the other 23. But if you wanted to make it exact with decimals, you do this: 83.3 seconds times 1 minute over 60 seconds, and then you would get 83.3 over 60 would be an answer in minutes, and it would be a fractional answer. What I did instead was I said, I'm going to take away 60 seconds from the 83 because 60 seconds is a minute. And once I take away 60 seconds, I'm left with 23, right?
Yeah.
That's what the 23.3 is. That's not really a conversion there more than it is knowing that 60 seconds makes up a minute. Lauren?
So like, I'm just confused where like, you couldn't just multiply 1.5 times 5? Like, can't you, like, it's like,
Well, look at the formula, Lauren. That's the reason you have to look at the formula. Go back to the top, okay? You have v equals x over t, right? See on the top left? And you want to get t by itself. The only way to get t by itself is to multiply by t and divide by v at the same time. Or switch those two, remember? So it turns out to solve for t, it's x over v, not x times v. Okay? If you were solving for x, x would be v times t. That's where it would be multiplication. All right. With that said, take a look at your homework, please. So we're going to transition over to the lab in a moment. Let's talk for like maybe 2 minutes about things in terms of responsibilities you have. This is your homework, okay, in this section. When I assign homework from a section, it's usually almost due every time the day after. So this homework will absolutely be due tomorrow. Tomorrow is Tuesday. Your lab that we will do today will not be due until after this test. So you don't have to worry about the lab besides what we do in class, okay? So homework is due tomorrow. Tomorrow, what do you think? Tomorrow, for you guys, tomorrow's Wednesday?
Yes.
So let's do this. Let's make it more reasonable. Let's make the problem sets, because they're due tomorrow already. We'll make this homework due Thursday. Is that clear?
Yeah.
So I'll put it on Moodle. So you can write it down now, but I'm going to put it on Moodle. Problem sets will be due tomorrow. I'll make this homework due Thursday. So tomorrow you're going to turn in the problem sets. Let me go to the problem sets real quick so you can see this.